Have you ever stopped to think about the invisible rules that literally run our entire universe? And no, I'm not talking about some sci-fi stuff. I'm talking about energy, heat, and work, the fundamental forces that power everything from a roaring car engine to the very cells in your body. Today, we're diving deep into the fascinating world of thermodynamics. It really all starts with a simple observation, something we've all experienced. Why does a running engine get so hot? Or why does just rubbing your hands together create warmth? You feel it every day. And the answer, well, it lies in the elegant and unbreakable laws of thermodynamics. So, at its core, thermodynamics is really the study of how energy moves around and, maybe more importantly, how it changes form. It's the science that explains exactly how we can take the chemical energy that's locked inside fuel, turn that into heat, and then convert that heat into the motion that actually gets us where we need to go. Okay, so to really get a handle on the laws of thermodynamics, first we've got to meet the key players in this whole game. First up, we have what's called internal energy, or U. You can think of it as all the random, jiggling energy of the molecules inside a system. Then there's heat, which we call Q. That's the energy that flows from a hot thing to a cold thing. And finally, there's work, W, which is the useful energy that actually makes things move, like a piston in an engine. And these three, they're in a constant, delicate dance with each other. All right, let's dive into the first big rule, the first law of thermodynamics. It's actually pretty simple when you break it down. Just think of it like an unbreakable budget for energy. And that entire budget is captured in this simple but incredibly powerful equation. Now, don't worry, it looks way scarier than it is. All it's saying is that the change in a system's internal energy, that's the delta U, is equal to the heat you add to it, Q, minus the work that the system does, W. In other words, you can't just create energy out of thin air, and you can't make it disappear either. It just gets moved around. So if you add heat to something, that energy has to go somewhere, right? It either increases its internal energy, making all those tiny molecules jiggle even faster, or it gets used by the system to do useful work. Now, this is where it gets really cool. This slide frames the whole law as a personal budget, which just makes it click. Look at this table. Adding heat, the plus Q, that's like your income. When the system does work, plus W, that's your spending. And the change in internal energy, delta U, well, that's what's left over in your savings account. You can't spend more than you earn unless you dip into your savings. It's really that simple. So if energy is a budget, how do we spend it to build things that actually do stuff for us? Well, let's look at how this law applies to maybe one of the most important inventions in all of human history, the heat engine. A heat engine is pretty much the first law in action. Its entire reason for being is to take a source of heat, like burning gasoline, and convert as much of it as possible into useful mechanical work, like, turning the wheels of your car. Heat engines all operate in a continuous cycle. First, they absorb a bunch of heat, Q sub H, from a hot source. Think of it like a tiny explosion in a cylinder. Then, they use some of that energy to do work, W, like pushing a piston down. And finally, and this part is absolutely crucial, they must reject the leftover energy as waste heat, Q sub C, to a colder place, like the cool air outside your car. So how do we know how good an engine is at doing its job? Well, that's where something called thermal efficiency comes in. It's just the ratio of the useful work you get out compared to the total heat energy you had to put in to begin with. In other words, how much bang do you get for your buck? Okay, so if we can turn heat into work, why can't we just build a perfectly efficient engine? Why is there always some waste heat? That brings us to the famous second law of thermodynamics. You see, there's always a catch. So the whole point of the second law is this. You can never, ever have a perfect engine. Nature puts a hard limit on how efficient we can be. It is physically impossible to take heat from a hot source and convert 100% of it into useful work. You have to throw some of that heat away to a colder place. Waste isn't some design flaw. It's a fundamental law of the universe. And that's really the bottom line. A perfect, 100% efficient engine can never exist. It would violate this unbreakable rule of how our universe works. And that has massive implications for, well, everything, from engineering to our global energy strategy. But now, let's totally flip the script. We've seen how flowing heat can create work. But what happens if we use work to move heat? Let's talk about refrigerators. That's exactly what a refrigerator or an air conditioner does. It's basically a heat pump. It uses work, in this case electricity from the wall, to force heat to flow against its natural direction. It's literally pumping heat from the cold space inside your fridge out into the warmer air of your kitchen. And this slide just perfectly illustrates that relationship. In a heat engine, the natural flow of heat from hot to cold is the input that gives you work as an output. In a refrigerator, work is the input that forces heat to move from cold to hot. The roles are completely flipped, but it's the exact same fundamental laws making it all happen. So, what does this all mean for us? The laws of thermodynamics aren't just some abstract physics problem. They govern our entire reality. They tell us that every single time we convert energy from one form to another, there's a cost. Waste is simply unavoidable. So, knowing this, how do we innovate within these unbreakable rules to power our world more efficiently and sustainably? That's the real challenge these laws leave with us.